As an example, I'll calculate here the location of L2 for the moon going around Earth, and L2 would be lying on the far side, and perhaps the interest to put a satellite there would be one that monitors the far side of the moon. The equation looks virtually the same with the exception of this plus right here. There is a minus in the equation that you use, and it comes from that for your equation that you use with L1 lying in between Sun and Earth, the two gravitational forces are subtracted. And here, because Moon and Earth are lying on the same side of L2, the two gravitational forces are added, and really the only thing that changes for the whole equation is that there used to be a minus, and now in my example there is a plus. Okay, so here's the equation. Let's first calculate this one here, 1 plus the mass of the moon divided by the mass of Earth. So for that I looked up the mass of the moon and the mass of the Earth. I divide the two and I add that to 1, and I come up with 1.012316, I guess, rounded, for that coefficient in the middle of the equation. By the way, for the one that you're going to calculate, I divided the mass of the Earth by the mass of the Sun, and I come up with 0.999997, and that's written in the on the lab sheet, so you don't have to do that calculation. It's already a 0.99997 with that minus in front of the coefficient. Look at the equation. The same as with my factor, the 1.012316, that also has a minus in front of it. So now I'm going to this online calculator for quintic equations, and I'm going to put the coefficients in, and the one for r to the fifth power is 1, and that's what I said in the text. You kind of have a 1 in front of it. Don't put a 0 there because it's not. It's a 1. And then the 1 in front of the r to the 4 is a negative 2. The 1 in front of the r to the third is 1. The 1 in the front of the r squared, that's a complicated one. Starts out with a minus in front of the parentheses, and then 1.012316. So I finally rounded it. The one in front of the r is a 2, and then the last one is just a negative 1, and then I have it calculate just to 6 decimal places, and I come up with 1.168 168186. But I basically just going to look at the first couple of digits here, the 16 or rounded 17, and that means that L2 is lying 17% further out than what the moon's orbit's radius is. So take the moon's orbit's radius and multiply it by 17%, and that's where L2 is going to be. I'm going to do that here. So the moon's orbit's radius is, or semi-major axis actually, is 384,400 kilometers. I multiply that by the 17%, so pi 0.17, I come up with 65,000 kilometers. I found a reference on the internet that looks as follows. So here at this question and answer website, curious.astro.cornell and so on, you can see that they posted 60,000 kilometers, and they call it the Hill sphere, and they explain the Hill sphere being under the influence of one body rather than the other. So that coincides with the number that I came up with. So you have to do the same thing for the L1 point that lies between Earth and the Sun. Notice that I came up with 1.17, and then I used the 0.17 as a percentage. You're going to come up with a number slightly smaller than 1. So for example, if you came up with 0.92, then you would use the difference of 0.08, 8%, as the distance that L1 would be from the Earth. So 8% in that case, if that's the correct answer. By the way, it's not. So 8% of one astronomical unit.